All right. Ooh, wrong thing there. Welcome back, everybody. And we're going to get into this next section, section 9.2a, on hypothesis testing for proportions. We're going to actually go through the whole process. Now, if you recall from last time, we did, at least in class, we did an example where we're testing out my free throw shooting skills. And like, I claim to be an 80% free throw shooter, but we might believe that this is exaggerating. So to test the claim, I attempted 50 free throws. I only make 32. That's 64%. Is that enough to say that I'm actually a liar? And we kind of went into the idea like it could have just happened by chance, but we're trying to find the probability that it did just happen by chance, that I did just have an off day. So we did a whole bunch of simulations of 50 shots. Here's an example of a bunch of them. This is 400 sets of them, and the proportion of made. And really, 64 is right here. If you can see in the circled section, that's only 3 out of the 400 total trials that had happened that way, where it was 64% or less. And that's not real great. Like, that's a real small percent chance that it could have happened by chance. Which means that's significant, and it probably didn't actually happen by chance. There's probably a reason to it happening that I'm not actually an 80% free throw shooter. Now, we're not going to do simulations over and over again. It just doesn't make sense to do that. But what we're able to do is a significance test based off of things that we already know how to do, like using a normal curve. Excuse me. So, we are going to do that today, and we're going to talk about some of the differences between doing this simulation and how we can just run this significance test. All right? So, quick review of a couple things. By the way, this is section 9.2a on hypothesis testing for proportions. A couple review of sampling distributions, because we're going to base it off of the idea of sampling distributions for probabilities, p-hat. Okay? The mean of all the proportions, what did we say the mean is going to be equal to? The mean of all the proportions would be equal to the actual true proportion. Where it changes a little bit is the standard deviation. You can find this on your formula sheet, but the standard deviation is the square root of P, Q over N. For a confidence interval, we used P hat, Q hat over N, and we're going to be using a similar thing here. The Z value. Remember, Z value is always like a test statistic minus the actual parameter, all divided by the standard error, or the standard deviation. So in this case, if we were doing that, it would be P hat minus P over everything we just wrote, which is the square root of P, Q over N. So that actually helps us build a formula that we're going to use, and we could go back and use that with the same scenario with the free throws, as long as certain conditions are met. So remember, we're looking for random sample or random assignment within a group. All right? Random sample from the population or random assignment to treatments. I suppose if it's two proportion, we can do that. We're typically just going to have the random sample now. In order to use, to correctly find the standard deviation, to correctly use a z-table, we need to know shape and we need to know independence. So we do need the n times p is greater than or equal to 10 and n times q is greater than or equal to 10. That allows us to use that. We also need that 10% condition when sampling without replacement. We can't assume independence unless we have that condition met. N has to be less than 10% of the population. So same conditions we've been dealing with. And those are going to be the same conditions we're going to continue to work with today. Now, as a review, I had this on at the end of the last video. You should know the recipe for hypothesis testing. And this is it. Okay, we've worked on the parameters and the hypotheses. We've talked about the p-values and drawing conclusions. We want to continue that and also find the p-value from what we're given. All right? So these are going to be all the same, pretty much all the same as the, very similar to the same as confidence intervals. It's also going to be all the same for other tests that we're going to do. We'll just change the actual test. Sometimes we'll use a t-test, and we'll get into that at a later time. All right? But when carrying out a significance test, we're going to use sample data to measure the strength against the given or the assumed, the null hypothesis. And something is worth noting. The test compares a statistic calculated from sample data with the value of the parameter stated by the null hypothesis. So that's what I was just saying. Values of the statistic far from the null parameter in the direction specified by the alternative hypothesis will give us evidence against the null hypothesis. So a test statistic measures how far a sample statistic is actually away from the null. And this part right here will be on your formula sheet. It just gives the general idea of a test statistic. We've always been working with z's, right? Z score is x bar minus, well, I guess it depends on the thing. The statistics minus the parameter. It could be x bar minus mu. It could be p minus p hat minus p. Divided by the square root, or sorry, the standard deviation, which changes depending on the situation. Specifically for one proportion z-tests, we're dealing with proportions, and we're dealing with those things we just reviewed. So to find our test statistic, which is going to be a z, it's going to be p hat minus p divided by, and I wrote this before, the square root of pq over n. And it's going to have to be, we're going to use the p and the q from our null hypothesis. Okay? So we'll talk about that in a second here. So let's start with the first 4 steps of that. So it says Hershey's claims that 80% of people love chocolate. That's their claim. In a simple random sample of 82 people, only 60 said that they love chocolate. That's less than 80%. We want to test that claim at an alpha level of 0.01. So it's important to note the alpha level. So we want to start by stating the parameter, identifying our hypotheses, naming the test, and checking the conditions. Those are going to be always your first things before you actually get into getting the numbers. Okay? So I would start off step 1. This is a proportion. So P equals the true proportion of people who love chocolate. Our hypotheses for these, we always will have a null hypothesis and an alternative hypothesis. And they're based off of the parameter. So the null is that P is equal to 0.8. That is the claim. But based on our evidence, we might think P is less than 0.8. And we are going to test that using a 1 proportion z-test. Now, before we get into actually doing the test, we need to check those conditions. All right? What conditions do we need to check? Dealing with proportions, we still want to, if we're doing this 1 proportion z-test, we want to check to make sure it's a random sample. In this case, random sample of all people, which is pretty easy to do. It was given, it was stated that, so we can say it was stated, yes. Check that 1. All good. Number 2, we need to check n times p and n times q. So there was a sample of 82, and 60 out of the 82 said that. So that's our p. Actually, hold on, that's our p hat. Now, since we're testing against the parameter, we actually have to use the parameter. So we're going to use p equals 0.8, q equals 0.2. Common mistake would be using the the sample, but since we're testing against using a parameter, we're going to use that in our stuff. So there was a group of 82 people, 82, and we're going to use times p. That gets us 65.6. 82 times 0.2, so p times q, that gets us 16.4. Since both are greater than or equal to 10, we're good to go on that one. And lastly, the 10% condition. It is sampling. We do need to check this. Is 82 less than 10% of all people? Absolutely. We can just say yes. So our conditions are all met, which means we can then continue with the rest of our significance test. Okay? And that's where we actually get into that formula. Okay, so step 5 is write the formula, plug in, and crunch the numbers. Now our formula is going to be to get a z-value so that we can get a p-value. So our z-score, our test statistic, is equal to p hat minus p, and this is written before, divided by the square root of pq over n. And in this case, it will be 60 over 82. That is our p hat minus 0.8 divided by square root of 0.8 times 0.2 divided by n, which is 82. Crunch the numbers in your calculator, you get a z-score of negative 1.546. Now, how do we get our p-value from that? It's technically step 6, is get your p-value. To do that, we're going to just go, you can either use not inverse number, you can use normal CDF, or you can use your table. But the probability that, in this case, it's our p-value, that z is less than negative 1.546 is I got 0.0606. Now, here's something I want to go back to, because I was just thinking about reading the problem. It's just asking if the company's lying. Now, I stated that my alternative hypothesis was that it was less than 0.8. You could very easily argue, because I don't know that, it doesn't say specifically that we think it's less. It just asks if they're lying. So this probably should be a not equal to, which means it's a two-sided test. Now, ultimately, it won't matter either way with the p-value that we have. But because we got 0.0606, our actual p-value is going to be 0.0606 times 2. Oops. I apologize for that. I'll fix that. 0.0606. We'll multiply it by 2. We'll say it's a two-sided for this one. And you end up getting 0.1221, I believe, if you kept it in your calculator, times 2, or 1212. Depends on if you use normal CDF. So from my table, I got 0.0606, so it would be 0.1212. If I use normal CDF, I got 0.1221. Slightly different, not going to make a big difference in this case. So that's our p-value. Now we want to reach our conclusion. Okay, that is not super low. It is low, but it's not super low. So in our conclusion, make note, we want to compare the p-value to alpha. We want to say whether we reject or fail to reject the null, and then what does that give us in context? So I'm going to give you this right here as a reminder of things to have. Basically, we want to say because whatever p-value is greater than or less than our alpha, that's what's going to go in here, we would reject or fail to reject the null. We do or do not have convincing evidence of that the blank, we'll say context with our alternative hypothesis. So if I go back to the example here, I would say, I'm going to write it like this: because 0.1212 or 21, depending on what you used, is greater than 0.01, our alpha level. I'm going to actually use alpha equals 0.021. So it's greater than that. I wrote it 2 now instead of 1, 0.01. Because it's greater than that alpha level, we do not have evidence. We fail to reject the null. That is our statement from the numbers. Now we want to go into context. We do not have evidence that the true proportion of people who love chocolate is different than 80%. That's that not equal to. If you were making your alternative hypothesis that is less than, then we would say that it's less than 80%. That is my conclusion. That is how I'm going to end this significance test. Okay? So, in general, I want you to keep in mind all these steps lead to a conclusion. The final step is rejecting or failing to reject and giving it in context. If you reject it, you have convincing evidence that your alternative hypothesis makes sense and that we couldn't just have that null hypothesis by chance. If you fail to reject, you just don't have that evidence. But it's important to note that a fail to reject decision does not mean that we're going to accept the null hypothesis. We don't know if it's exactly 80%. We just know that we can't say that it's not 80%. We don't have enough evidence against it. So that's why we use the term fail to reject. All right? And that pretty much covers the steps in a significance test. So I'm going to leave you with this. If you want to try this, you can pause this. This is another example if you want to try one on your own. It's specifically talking about high school teenagers using YouTube. Let's just say we did a sample at Hamilton High School and we found these numbers. And the alpha level in this case is not 0.01, it's 0.1. So do a significantly higher proportion of Hamilton High School students use YouTube. This is where you would use a test. It says test at that level. Go ahead and try it. For those of you who just tried it, I do have an example here of it being done. And if you want to take a look, compare yours, see if you made any mistakes, see if I made any mistakes, but I'm going to leave it with that. This is day 1 on significance testing, doing the whole process for a hypothesis or a significance test dealing with proportions. Spend a little more time on this next time, and then we'll get into 2 proportion ones. See you next time.